calls are the primary mechanism by which user space programs interact with the Linux kernel. Given their importance, it's not surprising to discover that the kernel includes a wide variety of mechanisms to ensure that system calls can be implemented generically across architectures and can be made available to user space in an efficient and consistent way. Okay, so I've been working on getting FreeBSD's Capsicum security framework onto Linux. Apparently, this is some bespoke framework for FreeBSD, as this involves the addition of several new system calls, including slightly unusual execv system call. I found myself investigating the details of their implementation. As a result, this is the first of a pair of articles that explore the details of kernel's implementation of system calls, or in short, syscalls. This article will focus on the mainstream case, the mechanics of a normal syscall, which is I think we are inspecting the read system call, together with the machinery that allows x86-64 user programs to invoke it. The second article move off the mainstream case to cover more unusual syscalls and other syscall invocation mechanisms. Okay, so we'll read the mainstream case. System calls differ from the regular function calls because the code being called is in the kernel. Differ from, it's not like a regular function call. The actual code that you're calling is already written on the kernel, and you essentially invoke whatever that kernel's definition of that syscall is, right? Okay, so special instructions are needed to make the processor perform a transition to ring 0. So privileged mode, or otherwise called as, you can call it as kernel mode, right? So most programs you operate in two, the system, you operate in two modes. Either there's user mode and kernel mode, right? Or privileged mode in this case, right? So, and there needs to be some processor way of identifying how you go to that privileged mode. Makes sense. In addition, the kernel code being invoked is identified by a syscall number, okay, rather than by a function address. Okay, so there's no address, so there's a syscall number. Okay, defining a syscall with a syscall defined. So this syscall underscore define n. The read system call provides a very good initial example to explore this kernel's syscall machinery. It's implemented in fs/read_write.c as a short function that passes most of the work to vfs_read. Okay, do we want to go read this one? We can, but we will try. I don't know if we would understand a lot of it. Let's see. So this is the read call. So this is a function descriptor. They have an fd get underscore post. I'm assuming this gets the position of the so not the function descriptor. Sorry, I misspelled that. I meant file descriptor. So this gets a file descriptor, and then this creates a return. So I'm assuming this looks like a an error code, right? ebdaf. Okay. See what that means. Yeah, it's a bad file descriptor. So essentially what this function does is they're saving this as the return value, right? And then if there is a file, they do a file position read, I think. I'm assuming this. So this is a position, and this does a vfs_read. Again, I don't know what this function does. So if there is so essentially I think this if this is able to read this file, so if the read syscall is able to read use the vfs_read file, and then able to read that particular file with a buffer of, I'm assuming this is the size, right? There's a count. I don't know what this count is used for, but okay, and the position. Again, this is the file descriptor's position, is it? So if the return value is greater than or equal to 0, they do a file position write, and then pass in the position fd put of position. I don't know what these functions do either. But if none of this works, so basically if there is no file, if you're trying to read a file that is not there, it returns the this error code, which is a bad file descriptor error, right? So that's what it returns. Okay, I think, do we want to read more into what each of these things do, or shall we go back?
No, if you could look at the FD structure.
Sorry?
Maybe. The line number 5 and 3 struct FD.
You want to look at what exactly here? I mean, we can ask ChatGPT to explain this to us. Right.
Let's do
that. This is mostly because we don't understand the internal workings and. Yeah, so it's reading from a file descriptor to a buffer, so it's breaking this down for us. So syscall define 3 is a macro. defining with 3 arguments. Okay, so just this is a good thing, right? So what we read was the syscall underscore define n is the signature for that particular system call definition, right? And if you say 3, that means that you'll have to provide 3 arguments. But I see more than 3 arguments, so that is something that I don't understand. So let's see. So unsigned int fd is the first argument, which represents the file descriptor. Okay, makes sense. Sorry. So this is the first argument. So this is the function name itself. Got it. So unsigned int fd is the first argument. Oh, okay. So this, okay. So now I understood. So this definition looks like the actual. So this is the syscall that you're defining. This is the first argument. This is the variable name for that argument. This is the second argument. This is the second argument's type, and this is the variable name for that type. This is the third argument, and this is the third argument's variable. This is the third argument's type, and this is the third argument's variable name. Right. So that's how this is sort of a comma separated value. Sort of like in the syntax here is comma separated values of the type and the actual like variable name. Right. I think that makes sense. So so the user part here is marked is a marker used to the user. Okay, so let's read this from here. Which is the first argument represents the file descriptor from which the data is to be read. A file descriptor is a handle that is used to access a file or a input output source. So char double underscore user star buff is the second argument pointing to the buffer wherein the actual the red data is going to go into this buffer, right? It should be stored. The double underscore user part is a marker used in the kernel to indicate that this pointer refers to memory in the user space, not in the kernel space. Okay, this is important for safety and security as it prevents direct access to kernel memory from user space. Okay, and size t count is the third argument specifying the maximum number of bytes to read. So this is the maximum, like this is basically the size of that file. So the max of that, whatever max allowed file size that you want to read, right? Or the max buffer size, or like that's what it says, the max buffer size, because the buffer size is going to be the number of bytes that you're going to read. And so the other question we've had was, what do these do, right? So fd so this again, so as we mentioned, so this this is called to retrieve the file descriptor and its current position. So it returns a struct that contains a pointer to the file object, which is f.file, and the current file position. This is necessary because the reading from a file typically advances the file's current position. So knowing that and updating this position is essential. So what does a file's position here mean actually?
What I wanted to ask, like, what does this like break down the line function word, like the struct below. So yep, this line.
Yeah.
Struct. I understand you're trying to define a struct now. FD. Okay, what is FD here?
FD is a file descriptor.
So you're saying that the structure of file descriptor for the variable f is equal to this function call. Yeah,
correct. This function call. That's correct. So the FD is the file descriptor struct. That's already defined. So this is already defined in C. So you're just instantiating that with a variable called f, and then the value for that is basically whatever this returns, right? So that is called to retrieve the file descriptor and its current position. Returns a structure that contains returns a pointer to the file object. So f.file and the current file position. So again, so does someone know what the current file position means? Probably because I don't work with this. So what does a refer to?
It's when you're passing the file, right? So what happens is in the file where the position where your current handle is, right? It's the position in the file. That's what it means. You read it.
Okay. Right. So it's the marker saying how long you've read a file or written. So right. That's a bit. Got it. Okay, this makes sense, right? Because if you've already read the file, that's it. The marker is going to be offset by some positions, right? So that is what this is used to get. Got it, makes sense. So if there's a file descriptor, so this essentially what this means is that if you've already read a file, it's already at some position, right? So this gives the pointer to that position. This is again initialization. This line is initializing it to EBDF, which is the error bad file descriptor. This is to so that So basically it's an invalid file, or the file does not exist or something like that. I am assuming that this gets translated in upper layers to whether like to different types of error, but I'm not going to dive deep into that. So if f.file exists, basically if this pointer has some value, then we load that, essentially starts reading the actual position itself. So file position read is a file underscore pos underscore read, takes this f.file, which is the pointer, and then returns a position, right? So this is used for lof underscore t is used for file positions and offsets capable of representing larger numbers to support larger files. Okay, and so and then the return value. So the return value we set it to bad file descriptor. We are doing vfs underscore read, doing an f.file. So this again, vfs underscore read is the function that actually reads the. So up until now we have not actually read the file. Up until now what we have done is we have just read the file's position, right? And now what this vfs underscore read is going to do is going to actually start reading the file, and that what is it going to do? It is going to take the file that is written read from that, whatever the data it is going to read in terms of bytes, and then it is going to write that into this buffer, right, which is the variable that we initialized it with, and this buffer is going to be empty by default, right? And but it I think it reads the buffer until it does not overflow the number of count of bytes to read, right? And the what it returns is the position, or it returns a pointer to the current position. The current position is updated after the read operation. So this makes sure that, as we said, right, as a file is read, the marker essentially moves, and then it goes and after the file is completed reading, the marker is at the end of that file. So the position is updated to be at the end of the file. So now if this is greater than 0, that means that so the return value is there. So we start. Okay, so if the read operation was successful, the ret is non-negative, indicating the number of bytes read. If the new file position is returned back to the file object, and this updates the file's current position for subsequent operations. I think this makes sense, right? I think up until now this makes sense. fd put position, this is to release the file descriptor and its associated resources. This step is crucial for maintaining the integrity of the file descriptor table and preventing resource loss. So fd put underscore pos is here. I think we've sort of understood what this function is doing. Yeah? Any questions?
Yeah, we've understood.
Okay, so what we've learned is this is how you define a syscall for the read, and then it takes in a variable number of arguments with types and this thing, and based on whatever the actual syscall has to do, it returns it. Usually, if there's an error, it usually returns an error. Like, I'm just trying to form a structure for me to understand what a syscall definition looks like, right? Okay, so let's go back. So this is okay, interesting. They actually I guess this entire article goes through that, but okay, let's see. And now we actually have some cursory understanding for what the syscall itself does. So let's read about it. So the read system call provides a good initial example to explore the kernel's system syscall machinery. It's implemented here as a short function that passes most of the work to VFS read. That's what we understood. From an invocation standpoint, the most interesting aspect of this code is the way the function is defined using the syscall defined macro. So when I said function, I actually meant a macro. So here this is a macro. So what a macro is to understand from just a concept of a macro. Conceptually, what a macro means is a macro is already defined as what are the think of it as a function that is expanded in compile time, right? So it is not so there's already a function, and the moment the moment the code is built, right, think of this as the moment you're let's say you're using Clang or some compiler, right, and you're using this to build your out files, right? So the moment you start building, this macro is going to ideally be replaced with the full function definition. Again, this is my understanding based on Rust macros. That there could be some differences. I think they are called hygienic versus non-hygienic macros, but let's not go into that. But just from a cursory understanding of what a macro is you replace. Think of this as not a function call itself, but the entire function definition is sort of copy pasted from there, right? That's what you think of as a macro, right? I think that makes sense. Any questions? I hope that's clear.
Yep.
Cool. So let's read more. So syscall define 3. We read this, right? So these syscall define n macros are the standard way for kernel code to define a system call, where the n suffix indicates the argument code. The definition of these macros gives 2 distinct outputs for each system call. Syscall metadata, which is read 3 unsigned int fd character underscore user star, which is all the arguments, and then a syscall define x. Okay, this is another way of doing it, is it? Oh, okay. Okay. Oh, sorry. So it gives you 2 different outputs. So this gives you 2 outputs. One is called as syscall metadata. The other is double underscore syscall define x. So the first of these is syscall metadata that builds a collection of metadata about the system call for tracing purposes. It's only expanded when this syscall is defined for the kernel build. So now you get what I meant by the macro. So this expansion is what they're talking about, right? So and why this is so this metadata is also sorry about that. So it's only expanded when some config variable is set for the kernel build. So when we are building the kernel, if this particular config is set, they expand this this macro, or they don't basically expand this macro, because again expanding a macro takes space. It's also you're essentially expanding some boilerplate that is already there, right? So if you don't need the metadata, it's probably not required. So they do it based on some conflict flag, right? And its expansion gives boilerplate definitions of data that describes the syscall and its parameters, right? Okay. I guess that makes sense. So you have metadata and the actual definition itself, right? So syscall underscore define the part is more define x part is more interesting, as it holds the system call implementation. Once the various layers of macros and GCC type extensions are expanded, the resulting code includes some interesting features. So that's now you're starting to do ASM linkage. So ASM linkage long sysread. So this is the unsigned int file descriptor. So now you start seeing the actual this looks like a function itself, right? So here this was a macro, and for this macro we did command we did comma separated values of some sort, right? For the number of arguments and types. But here, so this looks like a function itself, and this is the ASM linkage. I'm assuming this is, I don't know what this is, but this links to assembly is what I can understand from this. So right, so unsigned int fd. Okay, these are all the arguments that we passed. There's some attribute alias. Okay, static inline long syscall underscore read. So again, this looks like this looks like a type to me, right? This looks like a type to me. These are all looking like type, and this looks like an actual the actual implementation itself, right? So so first we notice that the system call implementation actually has the name sysc underscore read, but is static and is inaccessible outside this module. Okay, so there is an internal implementation called sysc underscore read, and it is accessible only through a wrapper. Okay, the wrapper function is called sys underscore read. Okay, so this is the actual implementation, all right, and this is the wrapper function. And the wrapper function, so this is right, and that is static and inline. So which means that they are saying that you cannot access it outside this module. What is accessible outside this module is this guy. Okay, and it is visible externally. Looking closely at those aliases, we notice a difference in their parameter types. Sys underscore read expects the explicitly declared types, characters double underscore user star for the second argument, whereas sys underscore read, which is the actual system, which is the external exposed function, right? It expects a bunch of long integers. Okay, digging into the history of this, it turns out that the long version ensures that the 32-bit values are correctly sign extended for some 64-bit kernel platforms, preventing a historic vulnerability. Okay. So the difference here they are saying is they are expecting it to be a character star buffer, but here instead they are taking a long integer. So basically this is not taking in a double underscore user star buffer, but instead is taking a 64-bit integer, and this is done for some addressing some historic vulnerability, it seems. Okay. So the last things we notice with the sys underscore read wrapper are the ASM linkage directive. So this is a directive. Okay. So what is a directive? I vaguely remember reading about this, but let's just go back. So what's the it's used in the context of function declarers. It's a macro used to indicate to the compiler that the function should expect to find its arguments on the processor stack, rather than in registers or typical locations. Okay, so the processor stack is going to have this rather than, like, typically your variables are going to be stored in registers, right? That is where you would when you have function arguments, whenever you pass in function arguments, those are going to be found in the registers, right? But when you are saying ASM linkage, what I'm reading here is when you mention that specific directive, the macro mentions that the arguments are not in registers. You should instead look at the processor stack. Okay. You see, especially in the context of systems programming, the way functions receive their arguments can vary. Most high-level C programming relies on the compiler and underlying architecture's calling convention to do this. However, in certain low-level contexts like operating system kernels, it might be necessary to or desirable to bypass these conventions for various reasons, such as consistency across different architectures. So this is again the reason why we are doing this is because the kernel itself, the implementation needs to, the Linux kernel itself is the same, and they are having different distributions, say for example, and different architectures like say x64-bit and all of that it needs to support. For this to work across architectures, I'm assuming this is done. So this is done to support system calls and interfaces, but we know why we are doing this. So when the kernel is handling a system call, it needs to know where to find the arguments for the call. The ASM linkage keyword tells the compiler the function's arguments are passed on the stack. Okay. So here's a simplified example. So there's a syscall argv1 and star argv2 is declared in the ASM linkage directory. Argv1 and argv2 are to be found on the stack. Yeah. So I think it was just repeating what it said earlier. So I guess we got that. Where are we? So the sys_read wrapper. So this is the wrapper that we're talking about. The ASM linkage directive and the ASM linkage protects call. The kernel UB's FAQ explains that explained that ASM linkage means the function should expect its arguments to be on the stack rather than its register. So again, ChatGPT was helpful enough to actually give this context before we read it, so it's great. And the generic definition of ASM linkage_protect explains that it's used to prevent the compiler from assuming that it can safely reuse those areas of the stack. So there's some processor stack, right? And so where did we see I didn't see a protect. That would be
I think it's inside the read, the second line of read.
Okay, so right. So okay, so when you call protect with I'm assuming that this 3 notes the 3 arguments, right? This is the return type, this is the return value, and these are the 3 arguments. I think this looks like the definition of it. Should we read it? Fine, well, might as well. Yeah, so n is this is used by architectures to keep arguments on the stack untouched by the compiler by keeping them live until the end. The argument stack may be owned by the assembly language caller, not the callee, and the GCC doesn't always understand that. So we have the return value and the maximum of 6 arguments. So this is n is the return value. Wait, n is the, what does n denote here? Are we reading assembly now? Okay, I'm not going to read assembly. Sorry, it has to end somewhere, right? So I'm not reading assembly. I'm just going to assume that it does what it does, right? So at least from the looks of it, right? This looks like 3 arguments for me, or like 3. At least from the definition of it, let's see. It explains that it's used to prevent the compiler from assuming that it can safely reuse those areas of the stack. So we assume that these 3 variables are on the stack, and this is the return value, right? I'm going to assume that. That's what it looks like, right? Because this is the return value. So we are passing that as the this sysread has a return value which is coming from sys which is the actual underlying implementation. This is the wrapper. So this is the return value, and we are passing in the return value to ASM linkage_protect as the second argument. The first argument is the actual number of arguments that we want to read from the processor stack, which is where we have 3 arguments, which is the file descriptor, the buffer, and the count, right? I guess I don't need to recollect what these 3 are. We understand that. So so generic definition explains that it's used to prevent the compiler from assuming that can be safely reuse those areas of stack. Okay. To accompany the definition of sys_read, the variant with the accurate type. So this is the accurate. This is the one with the accurate type, right? So this is the actual types. So this wrapper function has more expanded types, right? There's also a declaration in the syscalls.h, and this allows kernel code to call into system call implementation directly, which happens in half a dozen places. Okay, calling syscalls directly from elsewhere in the kernel is generally discouraged and is not often seen. Okay, so this is like a misnomer, right? We just saw so apparently it's not supposed to be done that way, but that is how it is. Okay, they probably have their own reasons to do it, so I'm not going to diss at Linux kernel code because they know what they're doing. Okay, I think any questions, any discussions up until now? It's generally hard code to read, so like I'm just talking about things that I've explained, like I understood from the face of it, right? I don't assume any expertise here, but I guess we can discuss if we have any questions or comments.
I guess if protect wasn't used, then the compiler wouldn't know that. I'm just trying to. If protect wasn't used, the compiler wouldn't know that memory address in the process stack is not used, I guess, and it would have put some other thing on there and like corrupted it. I guess that's why we are doing it.
Probably. That makes sense, right? Like, okay, let's. What happens if? Okay, let's just talk to our good guy. So here, just gonna wait. Oops. Yeah, that's what I wanted to do. So, what happens if asm linkage underscore protect isn't used? Let's wait. It's good, man. It's able to at least it's able to get a lot of context. Indicate that the function's argument should be passed to either stack. However, the function asm linkage underscore protect mentioned in yourself does not exist in the sort of exists, buddy. But okay. Protecting the arguments of system call handled in so here it's saying that it's not there in the kernel. Okay, let's ignore that. The function were intended to provide additional safety, so now it's starting to assume stuff. Okay, I don't think that's right. ChatGPT's knowledge has ended. Okay, let's go. Let's.
Not good.
Oh
Not
man,
good.
so we have gone into the deep trenches. Nice. Hey, that's good, man. Like if it's that difficult to find, you might as well, right? So then that means we have to start reading assembly code, is it? Damn. That's. I up until this point I have not run into a scenario where I had to do that. But okay, wait. Let's pass on this assembly to ChatGPT and see this. Yeah.
Rather like pass it on to Claude.
Claude, I don't have Claude actually.
It's free. You can have free access.
Yeah, let me do labs. I think Perplexity has it, right?
Like don't use ChatGPT. वो बहुत जल्दी hallucinate करना शुरू कर देता है.
Yeah. Okay. So I'm using Claude 3 Haiku. You're talking about, right? Should I use that?
Yeah, चलेगा कोई भी. But
okay. So let's try. So we are trying. This is the first time I'm trying Claude. Let's see. Where is that? Okay. So let me copy paste this. Does it immediately get this context? Be good to see. Let's see. Oh, I like this, man. I like that it immediately formatted it. I can potentially lead to, okay, as used to protect the function arguments and return value from being modified by the compiler during the function call. It ensures that the function arguments and return value are correctly passed and handled, especially in the context of where the kernel needs to ensure integrity of data being passed. So that's where, okay. Without the compiler may rearrange or modify the function arguments during the compilation. I mean, at this point, we just have to assume that this is right? Like this. Our knowledge sort of ends here. So
don't question the LLM.
Yeah. Like, I mean, Google has given up on this, so it's not like we can. There's more people who are writing about it, right? But okay, it's not used as a. So the problem. So essentially, when you're passing these arguments from user code to kernel code. But this is itself kernel, right? Like this we are already in kernel land at this point, right? are we? No. Okay, so the file descriptor is coming from the username. Okay, these are all passed from the username. Got it. So when you do smlinkage.protect, they are saying that it stops it from rearranging it. Modify the return value leading to incorrect return values. Okay, this is a compiler optimization. I don't think this is a compiler optimization. Should we ask a different LLM?
Yeah. The ones which are like वो उसका comparison दिखाया था ना यार, वो क्या नाम था, डेबिन का comparison, उसके अंदर कौन से थे?
I didn't see. I forgot what it was.
Like I remember Claude from it.
Yeah.
Like I tried out Claude from there. मैंने
Is it Claude or Claude?
Claude, मैं Claude बोलता हूँ because it sounds similar to you know what.
Yeah. I have to mute this now. It's Claude, man. What happens
Claude.
with ASM linkage protection? See, now I lost my train of thought. That's all I can think now. What happens with ASM linkage underscore protect is not there.
ये perplexity का selling point क्या है सर?
This is their labs actually. This is their playground. Perplexity is aiming at an audience which is similar to Google's. So it's trying to get an think of. I don't know what their end game is, but the idea is that they are an answer engine, right? If you're asking, like, I've tried it and like you can ask it like obscure questions that you would not be able to get or comparisons where you would not be able to get like a direct answer from Google, right? Like
GPT where like I saw your workflow, like when GPT failed you came here. So is it like supposed to be more like? No.
I just know Perplexity. Generally, I use Perplexity, but I know that they had. I just saw their announcement that their labs.perplexity.ai is just their like playground, but their core product is this, which is just like a typical search engine, right? This is their playground because I know that they had Claude. Like I didn't want to like sign up and like you have to sign. I don't know if you have to sign up for Anthropic and all of that, but this works without signing up, right? So that's why I just went with that. But I like this user interface, to be honest. Like the way this is formatted is like just nerd vibes, right? Sort of like this about. But all of them, Mixtral is also returning the same response. I'm assuming safety. Stay safe when you're reading, when you're using ASM linkage, I guess. Okay, let's go back. Where was the... Did I... Yeah, okay. I guess, yeah. So let's... Oh, we still have a bunch to go. Okay. So hunting for callers of sys_read also points to the way towards how users pay reaches this function. For generic architectures that don't provide an override of their own, include /uapi/asm generic usted.h, just like a header file, includes an entry referencing to sys_read. Okay, so this is where this is referenced. So this defines as generic syscall number _nr read 63 for read. So okay, so if you remember from earlier, right, so syscalls have a specific number. So here the nr syscall the read syscall has a number called 63, and that's for the sys_read. So essentially when you define this, it's not defining it, but this particular syscall has this particular number. I'm assuming they are just associating that, and uses the double underscore syscall macro to associate that number with the sys_read function, which is the one that we saw earlier in an architecture specific way. So this is non-architecture specific. For generic architectures, they don't provide an override. They have a default implementation, and for architectures that have like an architecture specific implementation, they have a separate one, right? For example, ARM64, which is ARM64 architecture, uses the ASM generic _ unistd.h header file to fill out a table that maps the syscall numbers to an implementation function pointers. So ARM64 apparently has a way to store it in terms of tables, just for mapping between this particular number and this function, right? Okay. However, we are going to concentrate on the x86 64 architecture, which is what like your ARM is what Mac M1 Max are running, but typical Intel architecture is an x86-64 architecture, right? Which does not use this generic table. Instead, x86-64 defines its own mappings in this particular table, which has an entry for sys_read. So this is what this looks like. Okay, this indicates that read on x86-64 has a syscall number 0, not 63. Okay, and has a common implementation. So architectures can. So the second thing that we have learned is, first thing we learned is by default the number 63 is there, right? But architectures can that give their own numbers for syscalls, right? And in case of ARM64 they follow the same thing, but for the typical internal Intel 64-bit architectures, that number is 0 and not 63, and it has a common implementation for both ABIs. For I forgot what ABIs are. What are ABIs? Damn, I should have listened more in the architecture classes. Okay, we'll look at.
मेरे आधे दिमाग के ऊपर से जा रहा है ये सब, but I'm trying to...
no, but we're trying to make sense of it. That's the whole point, right? It's not like I'm understanding and getting all of this and I'm going to put all of this to use tomorrow. It's just that we are trying to make sense of it, right? It's just that we go from an understanding of 0 to 20. Sorry, or 0 to 5 from like 0. Like, that's the whole point, right? Nothing else. So namely sys_read. So the different ABIs will be, okay, now I'll have to ask it. What are just just a second. Sorry. Okay, so what did it say? ABS define application binary interface. Yes, that's what it is. So it's a key concept in software development and computer architecture that defines how different program components should interact at a binary level. Okay. So it defines how function arguments are passed between the caller and the callee, data type, sizes, restrictions. So it's basically an interface for computer architectures for defining rules and standards that dictate various aspects of functionality, calling conventions. Okay, let's go back. Where was I? Yeah, okay. So this has 0 and not 63. This is called table.sh. The script generates this header file from the table and specifically generating an invocation of the common macro for syscall_read. This header is used in turn to populate the syscall table, which is the key data structure that maps syscall numbers. So they don't have a direct table itself. They have a script that populates some table, and that table also has a different numbering for x86_64 architecture. Okay, got it. That's all we need to. This syscall invocation. Now we will look at how the user space program invokes the system call. So up until now, what we have learned is how a syscall itself is defined and how that particular syscall has a specific unique number and how that particular number maps to the actual syscall definition itself. In our case, we are using the sys_read, right? That's the function that we are looking at. Now from user space, now you have to start calling the syscalls. That is what the whole article is about. So this is inherently architecture specific. So that when it restores architecture, we'll assume 64-bit x86-64. The invocation process involves a few steps. So clickable diagrams here on the left may help with the is this clickable? Okay. See that left may help with the navigation. Is this because of Safari? Probably. They say this is clickable.
It's a diagram.
It's an image, right?
Image with embedded
Okay, so in the previous section we discovered a table of system call function pointers. The table for x86-64 looks something like this. Okay, that ensures that any missing pointer entries to sys_nis syscall. So here syscall pointer t syscall table underscore syscall max plus 1. Okay, equals to, so this is some, I can't read this of that immediately. Okay, let's try to make sense from this. So there's 64-bit user space, RX is equal to 0, and the syscall happens. This goes to the kernel, and the actual syscall happens. This goes to the generic code. right? And then the actual code. I think this is more readable. So if you look at it from the space, right? So you're in your user space, and then you have like in the user space is where you're going to start doing the syscalls. The system call is in x86-64 assembly. They have another abstraction over on top of it, right? And that abstraction then starts calling the generic code, which is this is architecture specific, right? Up until this point, this is architecture specific, and then that starts going into the generic code, and then that generic code has the read function that we earlier defined, and that calls the internal implementation, which was which is not available for other modules. So this is available for external modules, and like imagine other architectures. So if you have ARM or other architectures, they're all going to call this sys_read, right? But internally, that is going to call this implementation that is not available for others, right? I think this is more readable. So for the 64-bit code, this table is accessed from some entry from the system call assembly entry point. It uses the RAX register to pick the relevant entry in the array and then calls it. So this is the register. Sorry, no, I said registry. I meant register. Okay, so RAX is in the user space. We have it set to 0. We'll see what this register is about, right? And then calls it. Earlier in the function, the what happened? The save args macro pushes various registers onto the stack to match the ASM linkage directive we saw earlier. Pushes the various registers. Okay, so if you remember, right? So the ASM linkage directive now is used so that what is the main use case that we saw was to assume that the function arguments are present on the stack. So this particular macro, the save args macro, I don't see where the macro is being used here. Okay. Earlier in the function. Earlier in this, which function? Okay, so in this implementation they are saying, okay.
You can actually click on the diagram to look at the exact code. I think it's similar to what.
Oh, is it? Yeah. Okay. Now I got it. Okay, these are all clickable. Okay, makes sense. This is not
that,
clickable.
not that
clickable.
one.
Yeah,
this is like a file code.
Okay, so system when the user can syscall entry. Syscall does not have anything on the stack and does not change the stack pointer. It does mask the flags register first. Okay, so system call. So there's some bunch of registers. This is harder to read. I'm just going back. Okay, so it uses the RAX register to pick up the relevant entry in the array. In which array are they talking about? Table of system call function pointers. So this is the table of function pointers, and then shows the missing entries.
MSRLS. What is that?
Table is accessed from here. And from the system call assembly entry point, uses the RAX register to pick the relevant entry in the array and then calls it. Earlier in the function, the save args. Let's assume a couple of things. So save args macro is used for what we wanted, for to satisfy what the ASM linkage directive needs, which is basically take things from the registers and put it on the processor stack. Okay. Moving outwards, the system call entry pointer is itself referenced in syscall_init, a function that is called early in the system call startup sequence. So this is so system call has an init sequence that it needs to do. L star and R star live in a strange symbiosis. Okay, they both write to the same internal register. Star allows to set CS/DS on only a 32-bit target. L star sets a. These are two variables that operate on the same register. I don't know what CS and DS are. That's okay. The WRM SRL instruction writes a value to the model specific register. In this case, the address of the general system call handling the function is returned to this particular register, which is specific register to call handling the. Okay. So now this is the architecture specific thing. So we read all the generic stuff, right? Okay. Now I have some understanding. So every architecture, right, has a specific way of so in this case they have a specific register from wherein to call syscalls, right? So this is the user space code needs to initiate that syscall from somewhere in the user land, right? So for that, what it needs is they have this is system architecture, which is x86 has a specific place from where this like specific address from where this happens. So the address of the general system call handling definition is written to this particular register. So this is the hex value for that. So this is the address where that is there, and this is what is going to call the actual, like, this is from here, you're going from user mode to kernel mode, right? So put it to just trying to simplify this, and for my own understanding is, on the user land there is a specific place from where you initiate a syscall, right? And that for this for specific architectures, it is stored on a specific register, and for x86 it is on this particular register, msr_l star register, and that is the hex address for it, and that is the syscall instruction. From there you can start doing syscalls, right? Hope that's my understanding. That makes sense, right? Basically, this. No.
Okay. I can't understand it.
Okay, so let's go to TLDA. So sorry for burning your eyes. So you have user mode, right? So you're on user mode, right? You need to do a syscall, right? And this user mode, essentially, you think of this as you are starting to write a function that needs to do the sys_read. This is one I need to call from the user land, right? So user code needs to call this, right? Needs to call this. So I can't directly call this. This does not know where this exists, right? In the kernel, this exists somewhere, right? This cannot directly call it, because it's what we read here up until this point is it's not a function that you can directly call. So if you read if you just go back to the first thing that we read, system calls differ from regular functions call because the code is being called is in the kernel. Right now you're in the user space, right? If you define a function here, like let's say function A, so if I say a function A, right, and then I can call, like, A can reference function B, because this is in user space, right? Because I have defined it, right? Let's say I put this in a box, right?
Okay, samajh gaya. Yep.
This is in a kernel. Okay. Yeah, so this is now in the kernel, right? But for me to access in this kernel, there needs to be a way for me to do that, right? What is the entry point?
Okay.
Yeah, and that entry point is in your register. So this is the M star register, right? That they talked about. So just to finish that diagram, so now your function B goes through
We'll rather call the register. We'll rather call whatever function that exists in that.
Correct. And then actually make the kernel call. Again, this is my understanding. So sort of makes more sense for me, right? Yeah. Any questions?
Okay.
Cool.
There was another register, right? Like they mentioned, just besides the diagram. Roll up. There was M star and L star.
Okay, so do you want to? Okay, let's. I think it's easier for ChatGPT.
Let's ask them. Yep.
You want to try Claude? Let's do it.
Whichever tells us the answer. I don't have a preference.
Let's see.
I want to know what are these three registers being used for.
MSR star? Okay, Claude.
Meanwhile, we can reread the WRMS around.
Which one?
WRMS, the macro that defines.
What does this do, right? Okay.
The instruction writes a value to a model specific register.
Yeah, so it's from here. Okay, so the instruction writes a value to a model specific register. In this case, the address of the general system call handling function is returned to. So the address of the generic system call function is returned to this particular register. Right? So when you called this one, but for that you need to know what this argument means, right?
Oh, yes.
Okay.
I think
is to control the CS and DS segment registers during a system call. What is the CS and DS?
CS and DS?
What is CS? It's okay. The more we know.
Yeah.
code segment and data segment registers are the two of the data segments used in 64 architectures to manage memory access and protection. Okay, the CS register holds the segment selector for the current code segment, which is the memory region containing the executing instructions. Okay, when the CPU executes an instruction, it uses the value in the CS register to determine the base address of the. Okay, so CS register automatically updated by the CPU during control transfers, such as function calls. So when you have like an interrupt, yes, I was just going to talk. So there's an interrupt or system call. It ensures that the CPU is executing instructions from the correct code segment. So essentially, if you're defining some function, it's the data holds this the data segment register holds the segment selector for the current data segment. There's a memory region containing the variables.
Yes.
Okay. So essentially, function calls, system calls, and any interrupts go into the code segment, and all the variables, arrays, and anything that you load or store, anything that you need to do, that all of that go into the data segment. Right. So the code is where the function calls exist, and DS is where the actual variables go in. I think we should have probably known all of this, right? I don't know. I guess we read all of this.
I don't think I've never paid attention. मैंने तो किया ही नहीं है CS.
Yeah. We should probably have paid more attention. But okay, fine. We'll learn it now. So the MSR star register is used to control the registers during a system call or return. So the value being returned by MSR star is a 64-bit value, where the upper 32 bits represent the user mode, lower 32 bits represent the kernel mode CS select. Oh, so it's a bit. It is so it by itself is okay. So it's a 64-bit value, and so I'm assuming this is defined in C, dude. So I think I got it. So this is a variable that is defined, and it has a 64-bit value. The first 32 bits mean user mode, second 32 bits mean kernel mode. The configuration allows CPU to automatically load the appropriate CS and DS registers when transitioning between user mode and kernel mode during a syscall. So the value user.32_CS and kernel_CS are likely defined elsewhere in the kernel code, represent the appropriate CS selectors. Oh, this is a bit manipulation that is happening. Yes. We didn't see this. Okay. So what are we doing here? So when you do.
So what it is saying is that the first part of this 64-bit value is going to be for the CS segment.
The CS segment of the users, the CS segment of the user and this is the CS segment of the kernel. Right. Yeah. So and this is being bit shift. Okay. So this is what are they doing with the bit manipulation here? Okay.
And if that is not there, then we are going to use the kernel one. That's what it is.
Is to construct the value that is returned to the or converts the value to a 64-bit signed integer. Okay, represents. Okay, so when this shifts the 64-bit value by 48 bits, effectively placing it in the upper 16 bits of the 64-bit value. Okay. I got it. So this is so this code segment, right? This code segment, we need to take the first 32 bits and then put that in the first section of the 64-bit value. The reason is to align the user mode selector in the upper 16 bits of the 64-bit value. That is the MSR star register. Similar to the above step, that converts the kernel and it shifts it to the left by 32 bits. So this represents the code segment to the shift by 32 bit aligns the lower 16 bits. So the first 16 bits are now, so in the 16, so what we have done is essentially we have taken the 32 bits and then put that into the first 16 bits of the 64-bit register of which is M star, right? The final expression combines the shifted user mode selector and the kernel mode selector using a bitwise OR. So we have done a bitwise OR on the first 16 bits of the user mode code segment and the kernel mode code segment. We have bit shifted them. We have basically taken put them into the first 16 and the last 16 bit segments of the M star register, right? And this creates a 64-bit value where the upper 16 bits contain the user mode CS selector and the lower 16 bits contain the kernel mode CS selector. Okay, is then returned to the MSR star register using this function. This configuration allows the CPU to automatically load the appropriate CS and DS register when transitioning between. So this is how the switch is happening, dude, between user mode and kernel mode.
Yeah.
Okay, this is okay. So okay, let me write this down. So there's MSR star, right? So imagine this is 64. So let's write this. So it was MSR star, right?
MSR star, yes.
Right, so MSR star. So this is 64-bit. So 64-bit integer, right? So what
Unsigned
this?
integer.
Yeah, unsigned integer. Important. I can't spell today. Unsigned integer, right? And so in the user space, so you have this is a 32-bit code segment, right? And this is user space, user mode, right? And similarly, you have this in kernel mode. Okay, and so what this WRMS what is that weird looking function? WRMSRN. Okay. So what that did was, so when you take these two and then take these two, yeah, so now you pass them to this function, right, of m star. Let's take that line. Actually, I think it's important to have that entire line. So let's just, it's MSR underscore star actually. MSR underscore star. Yeah. So MSR underscore. Let's take this line. Yeah. So what they are doing right now is taking this, doing a bit shift, right? So taking this code and then putting there. So what that does is,
and basically it casts a 32-bit value into 64-bit value.
Correct.
But what it does is like shifts the user CS into
correct
into shift it more than the kernel
correct.
CS value.
Exactly. So now this very clever, right? Yeah. So nice. So bit manipulation is where it's at, man. Like whenever I see like really clever bit manipulation, like I know some, like there's some intelligent brain sitting behind who's doing it. So, or this might be just common stuff that we just don't know, right?
We just don't do it often enough. Like
so that this feels like very like clever to us, or like someone who knows like all of this is going to look at this and laugh at it, but it's okay. That's not the point. So this is going to be 16-bit user CS.
Is it 16?
It is. Yes, this is 16.
Okay.
16. Right?
But we've only filled 32 bits now, right?
Okay. Wait, I have the same question. Let's read. Let's go back. So, have they explained this? Oh, they're done. Okay. They didn't even explain this. Okay, let's go back. So what did Claude say? It said that the final expression combines the shifted user mode selector and shifted kernel mode selector using a bitwise OR. But okay, let's. So the question we have is this shifted it by 48, right? So if you shift this 32-bit, which is likely a 16-bit segment selector. Okay, so this. Wait. So this part converts the 32-bit into a. Okay, no, wait. So this we've already converted this to 64-bit. So you see
that is already casted first.
So it's already casted, right? So it's already 64 bits, right? Out of which this already it has only 32 bits, right? And that 32 is moved to the first 16. Right, so this shifts the 64-bit value left by 48 bits, effectively placing it in the upper 16 bits. What happens to the rest of the 16 bits though? That's what I don't understand.
No, what it is saying is, what I am assuming here is the value user 32 is just a name. It might not be 32 bits. It might just be 16 bits. Maybe. I'm not sure on this. Like hypothesis is only seen here. Guessing here that user 32.
No,
like
the user mode 32-bit execution environment is what it's saying, right? Anyone get what we are like trying to?
We are off with a difference of 16. Like we want to know if where are those 16 bits going?
What happens to the 16 bits missing in doing the bit shift? Again, I'm going to look back at this and this feels so stupid, but yeah, let's see.
We are probably missing something very
Yeah.
fundamental, but like first time reading this.
Are effectively discarded? Huh? What? Why? Wait. Then. Other parameters are specific registers. Instruction call causes the process transition to ring 0 and pass. Why? How is this discarding this? Okay. How is
Like this might be just be bluffing. Like I'm not sure if.
Yeah, I don't know. But it is sort of sort of correct here, right? So the alignment of the user mode and kernel mode defines the upper and lower speed is as it allows it. Yeah, we got. They're saying that it's not required.
Record नहीं है ऐसा बोल रहा हूँ. Okay.
So
मान लेते हैं ऐसा ही करना पड़ेगा. I'm not sure.
We'll have to read about this. Maybe
We'll have
while
to probably just assume it is not like.
yeah, because it looks like it's bit shifted, and from our base understanding, right? We have a 32-bit integer, right? And we are taking that and discarding. We are bit shifting it for 48. Sorry, we have a 64-bit integer. We have no, the thing is we have typecasted a 32-bit integer to 64 bits, right? Now we have 64 bits and we are taking that and bit shifting it by 48 bits, so that means that only the first 16 bits exist, right? That's my understanding. Yeah, sorry, last 16 bits exist, sorry. And for the kernel mode, the kernel code segment is the other way around. The first 16 bits exist. So apparently this is all is enough. Okay, well, I guess we'll have to move up.
Right? Basically, मान लेते कि चल रहा होगा. Yeah,
probably it's probably working. but I'll add a like in the description or something when this video actually comes out. I'll read more about this and see if I can make sense of it. Okay, so let's finish the argument. The standard ABI for 64 programs invokes a system call is to put the system call number into the racks register and the other parameters into specific registers. So the system call number for 0 for read, right? So we read the system call number here is 0, right? For read is 0, and that's put into the specific register called racks, right? So that's why it's 0. So in ARM, this would be 63, right? Or in another specific architecture, it would be a different number, right? So it's for this one, it is 0. Into specific register, RDA, RSI, RDX for the first 3 parameters. So they have 3 different registers, and these are all are named. And for all of these, for every parameter that you have, right? I guess that is why if you're understanding C at a very low level is super important, because now you're seeing, right, like how this is programmed into a sense that every register that you are passing into as a function, like every argument that you are passing into the read function in the syscall literally has specific registers that are demarcated for it, right? That's how low level this is, right? So this instruction causes the processor to transition to ring 0. Ring 0 again is kernel mode, to invoke the code referenced by the MSR underscore L star model specific register, namely system underscore call. The system underscore call code pushes the registers onto the kernel stack and calls the function pointer at the entry RAX. Okay, so so here right now it's a generic call, right? Here I mean, so it just does system. What it is doing is I have what is essentially doing is I have the function that the system call that I want to read in the racks register, right? So let's say this is racks, right? So racks has 0. So racks is the register. This has 0, and we know 0 means sysread, right? Right. So we know that. So what this does is when you do they don't specify the actual syscall to read. So instead what they do, they generically do system underscore call, right? So when system underscore call runs, so it looks at the racks register, right? And then figures out it actually needs to call sysread, right? So this again internally then goes and calls the actual sysread function.
Okay.
Makes sense, right?
Hmm.
So this is generic. This works generic in the sense that it doesn't actually specify the implementation, specify the actual system call to read. So what this allows you to do is you can have any number of system calls, right? And then just do the system like you can like think of this as sysread, syswrite, any number of system calls, right? And the only thing that needs to be there is the racks register to have the corresponding number, right? So this is the syscall number, right? So here 0 is the number, right? 0 is syscall number, right? So if this had 1 or some other value, when you just do system underscore call, it's going to look at the racks register and do the write operation.
Yes.
That makes sense, right? Simplifies things a lot. So system call pushes the registers onto the kernel stack, and why this is important is this register is now pushed onto the kernel stack is what they are saying. Okay, so that is something that we need to add. So this goes into kernel stack. Remember the asym linkage guy that we talked about earlier, and the actual this is called okay. And calls the function pointer at calls function point at entry racks in the syscall table, namely sysread, which is a thin ASM linkage wrapper to the real implementation of the sys underscore read that we saw, right? Now that we've seen the standard implementation of system calls on the most common platform, we are in a better position to understand what's going on with other architecture. That was a heavy one. That was a really heavy one. Not going to lie.
This was mainstream image from the other one.
This was mainstream. Exactly. This is mainstream. This is this is something that people know apparently. But again, this is pretty old, right? The fact that we're reading this today is, I guess, still fascinating. There could be some things that have changed in the kernel, but yeah.
I don't think they would have probably given
See.
yeah.
This is precisely the sort of well-written intermediate material that is needed to help noobs like me and the ninjas who haven't reviewed it lately. This is nice. Yeah, actually, the really good article, I would say. But they could have gone into detail about this, I would say. Like one thing I would probably missed is some explanation about this, right? That would have sort of helped us understand this. Or this was like too like high level for them to not explain. Maybe this was like too straightforward to look
basic.
at.
अरे ये तो समझ ही जाएगा.
So it is like
that.
too straightforward for them to like call it out explicitly, but we had to break our brains, right? But
Yeah.
we are I guess we are more noobs than these people are.
Yeah.
So it makes sense, right? It's defined for user space interaction gender. I'm just reading comments. I'm just seeing if there are any questions that we didn't look at. Attempted to be binary compatible to use some hardware. Okay. Such as taking switch to okay. Oh, so this could be a question, right? Why do you want, like, this is the question, right? Why do you want to put the values into a register, then switch to kernel mode, and then put those values onto the stack, right? That seems like a switch, right? Why is that happening? Mm-hmm. So doesn't it make more sense to keep the values in the registers directly until the real syscall function? Like if you want to push the values onto the stack, like let the registers, let the values be in the registers, and then like when the actual call needs to happen, then you push the values onto the stack. Why do you have to do the switch to ring 0 and then push the values onto the stack, right? So that's what the question is. Having the arguments in registers for ring transition means there's no need for fancy footwork to get at the user space stack memory. Storing the registers on the kernel stack allows the state of the registers to be restored on the return to user space. But once the parameters are available on the stack, there's no need to preserve them in the registers too. The syscall can get its argument from the stack and immediately use the registers. Can immediately use So storing the registers on the kernel stack allow the state of the register to be restored. Oh, okay. So basically, what they're saying is like, since we do the transition, you can basically free up the registers. The rest, you have taken those copies, the copy of whatever the values are on the registers are, and then you have put that on the stack, right? So that means that you don't no longer need to. Those registers can be freed up for other things, right? And because the ASM linkage now the ASM linkage underscore protect, like which Ninad asked, right? So that ensures that those values are on the stack before we call them anyway, right? So that means that so the syscall now use the ASM linkage directive makes sure that those are already on the stack, and we can call them directly instead of waiting for those values to be again. Now what happens is now you have to go back to user mode, get back those values from the registers and come back. So you have to do another switch, which is unnecessary, right? So your registers are immediately cleared up. Obviously, the arcs have to be under stack. I guess, yeah. That's all the questions there were. Yeah, I guess this is great. How long was this? I didn't keep track of time. An hour, probably?
Yep. Yeah. More than an hour.
More than an hour. This is going to be difficult to break up. I can't break this up because video up, I guess.
Do you break things up?
Sorry?
You break it up?
I can't. I don't think I can break this video up. I'll put it as is. So
Yeah, just put it as is. I think.
I'm going to follow. What is that thing that you said again?
The 16 bits. Missing 16 bits.
No. You were talking about a manifesto. I forgot. What is that?
Cult of Done.
The cult of done.
Cult of Done. Yes. Yeah.
It's
Cult
more
of
like for artists, to be honest. Like.
Okay.
But
I'm gonna
we can
follow
find
that.
some useful things from it too. Yeah.
I'm gonna try following that.
There is
Let's
a
see.
boilerplate video on it. Like that's where I was introduced to it.
Oh, okay.
You could probably just watch that video and have a cursory understanding of it. Like he sums it up pretty nicely. No boilerplate.
Nice. So how was this article? Was this too much? Was a roller coaster?
I'm not. Like once again, I'm not sure if I would ever need any of this, but it was nice. Like looking at just.
I would have probably not like given like I wouldn't have actually read this if I didn't have like a 5 or 6 people to help me like wrap my hand around it, right? So I guess I wouldn't have otherwise
understand a lot of this article.
That's entirely fine. The whole point is not to understand the article. It's just that you just have a cursory understanding of what syscalls are. I think now you know what syscalls are, right? Like your takeaway here in this video is you know what a syscall is. You know that syscalls have some number associated with them. They have an implementation that has this weird macro. You also learned what a macro is, right? To some sense, right? And this particular macro has like this comma separated values, sort of like a definition to it, and each macro has like does something, right? And this is and you know what an ASM linkage is to some extent. You understand that you understand that, and then you understand that based on different architectures they call this syscall in different ways, right? Let's not go dive into deep into what every architecture does, but at least from like a cursory understanding of this particular syscall does this, and this is how it calls and you also understand that how the switch between kernel mode and user mode is happening using a nice 64-bit integer, right?
Yeah.
We also learned that some of those bits might be discarded based on what Claude told us, but I guess we can ask someone, right? Like someone who understands. I think there might be people on Twitter. We can just probably we can ask someone who's like a Linux kernel expertise, who has some Linux kernel expertise, and then help answer this question. If I find someone who can answer this question, that'll be great. I'll try to do that. But but I think those are the takeaways from this video.
Yeah.
Rest of the folks, what did you think? Aditya, Sagnik? Aditya, you have a lot of noise going on your end, man. Yeah. I couldn't hear you. But yeah, if you have some issues with your mic, just feel free to put in chat. Sagnik, Ninad, what did you think?
Yeah, I mean, I understood what kind of have a cursory understanding, as you said, and yeah, I liked it.
Great. Okay, let's do more of that. Next article we will see.
Do you folks actually code in for kernel right now? Like Balaji or Ninad, like are you folks? I know Aditya was into front end, so probably like is anyone involved in low level development right now?
I'm not. We all work way high level above.
Way high up there. Yeah.
I recently went from Python to Go, and that's low level for me right now.
Oh, okay.
Okay. So, I've gone from
This feels like a completely different land. Like this feels like a different computer
the whole-
science. Yeah, like this is not what I would ever come
but this is that's the thing, right? Like the whole idea behind this thing was we try to read things that are usually out of our reach or things that we ignore, right? Like this again, right? Like why would I ever have to implement my own syscall, or like I don't think I would ever have to do that, but at least reading about it makes me like more aware of the system, or like appreciate the system that we're all used to, right? Like there's so much complexity behind all the scenes that like we are used to like 10-15 layers of abstraction, right? But sometimes it's just good to read about all of this, right?